I would like to start, though, with the disclaimer. So if we could go to the next slide. The Mars 2020 science team is actually quite large. It's on the order of 300 people or so. But what I'm going to show you includes interpretations that reflect scientific consensus within the PIXL instrument team. And I'll explain what the PIXL instrument actually is. And that team is composed of about 40 to 50 people. So I'd just like to emphasize that the consensus within the PIXL team doesn't necessarily reflect consensus within the broader Mars 2020 science team. And I guess the reason for stating that is mainly because most of the raw data that you'll see in the presentation have really only been worked over in detail by the PIXL team. We've just reached the point where we're preparing things for publication and now sharing with the broader team. So I just want to make sure that you don't walk away from the impression that everyone is necessarily okay with this. Anyway, so we can jump into the next slide, please. You may be aware that the Perseverance rover touched down in Jezero Crater in February of 2021, and that rover is equipped with a variety of fascinating and powerful scientific instruments. There are many cameras positioned on the rover, some of which I'll refer to today. But really, the data we'll be talking about most derived from what's called the PIXL instrument. So the next slide just emphasizes where that instrument is placed on the end of the arm. The PIXL instrument is, in essence, a micro-focus X-ray fluorescence spectrometer. And so this, combined with the capability to grind away the surfaces of weathered rocks and analyze fresh interiors, gives us some great potential in constraining textural relationships, mineral identification, and geochemistry. And so we can really unravel the history of these rocks, which are actually quite old. So most of the rocks I'll be talking about today were probably emplaced on the order of 3 to 4 billion years ago. Next slide, please. So just a few more words about the PIXL instrument. I mentioned it's a microfocus X-ray fluorescence spectrometer, and the beam of the X-ray through which we're sampling ranges from about 58 to 120 microns, depending on the appropriate energy. And that beam size is achieved using polycapillary optics. And the scans or maps that we collect can be acquired by a variety of combinations of step size. And we basically have two modes in which we operate: grid scans or line scans. The X-ray anode itself is composed of rhodium, and it operates at 28 kilovolts. And we're able to detect elements, detect and quantify elements when they're present in concentrations high enough, from sodium to cerium. And you can see on this slide a schematic of the PIXL instrument. So on the top on the sensor head is where the X-ray beam is output. And the position of the sensor head is actually controlled by a series of hexapod struts, which are finely tuned to achieve motion on the order of about 8 microns or so per step. On the end of the sensor head is also a micro context camera, or an MCC, which is high resolution camera that is also able to acquire spectral reflectance data on the surfaces we're analyzing, which is quite handy. And then there's also a floodlight illuminator and a series of grids that collect topographical information of the surface that we're analyzing to allow a more or less constant standoff distance during acquisition of the X-ray data. We go to the next slide, please. The other interesting and important thing that the PIXL instrument does is that it's able to acquire X-ray diffraction data. And this is worth talking about in a little bit of detail, because I will show some data that bear on diffraction. But I've represented that in a schematic here that will appear in a paper to be published in Science Advances, led by Mike Tice from the PIXL team. But we'll start off by saying that, the acquisition of the X-ray fluorescence data is an energy dispersive process. So we're transitioning through the energy of excitation, through which we're able to quantify the element concentrations. But if you think about how diffraction responds to that process, the Bragg condition can be achieved when the energy and the orientation of lattice planes can both be satisfied. And we've done some quantitative modeling of this process, and it turns out that the probability of diffracting or detecting diffraction from a randomly oriented crystalline grain within PIXL's view is about 96%. So if a material is crystalline, chances are we will capture some expression of the diffraction. The important thing to emphasize here, though, is that PIXL actually contains two detectors that are placed at small angles away from the center of the X-ray beam vector. And the location of those detectors is illustrated on the left-hand diagram by the vectors GA and GB, which are meant to represent the direction of vectors normal to diffraction planes that would be acquired in those detectors. And the fact that there are two detectors is quite useful because it means that the orientation or the angular dependence of the Bragg condition can potentially be met by one of those detectors during the time that we scan across the energy range. So the combination of that angular dependence and the energy is represented in the left-hand diagram. And then on the right-hand diagram, it's just a schematic meant to represent what or how diffraction can be manifested in a typical PIXL X-ray energy spectrum. And so you can see that the signals from either detector A or B will be different. So one of them will pick up the diffraction condition, but not the other. And here, a normalized structure factor from the constraints from the left-hand panel is just used as a proxy for the intensity of diffraction. The other important thing to note about the diffraction when it's observed by PIXL is that it can only be observed for crystalline materials on the order of 20 to 40 microns in size. So that's actually quite useful. So that, combined with the probability of detecting diffraction on the order of 96% or so, means that if we don't see diffraction from a surface, it means that the material is either finely crystalline or poorly to non-crystalline in nature. So that's an important caveat to mention before I show some of these data. Okay, so we can move on to the next slide. Yeah, so a little bit about geological context. So I mentioned that the rover landed in Jezero Crater, and this is a geological map put together by Sun and Stack in 2020 that gives a sense of the units that are exposed within the landing ellipse and the landing site. So you can see the Arcuate Mountains on the left-hand side colored in brown that sort of circle around the rim of Jezero Crater that are uplifted. And then, of course, there's a deltaic deposit that's represented in blue that is deposited from the northwest. You can see the landing site illustrated by the black dot. And so for most of the initial part of the mission, we spent time surveying the Jezero Crater floor, which is mostly dominated by these pink and orange colored units that I'll talk about in a little bit more detail. But you can see that the landing site was conveniently positioned near what's been interpreted as a geological contact between a salmon colored unit, that is the so-called CFFR unit, and this more orange colored unit. So if we go to the next slide, you can get an orbital view of the traverse from the initial part of the mission. And this traverse basically follows that interpreted contact between two geological units. So you can see located in blue is the Octavia E. Butler landing site. And from there, we ended up circling south and focusing on targets that were outcropping from two different geological units. And can I go to the next slide, please? And so this next image just gives a sense for some of the targets that I'm going to talk about today and where they're located. So on the upper left-hand side, panel A, that is a representation of the geological map I just showed, showing the zoomed in area in panel B. Panel B shows the traverse from the initial part of the mission, and I'm going to talk about data that were acquired from three targets. So these were rocks that we encountered where we abraded the surface to expose a fresh surface underneath, acquired a variety of data sets with the PIXL instrument and other instruments, and in most of these cases, we're able to extract sample cores successfully to be returned by a future mission to Earth. The bottom panels C, D, and E are high resolution images taken of the abraded patches around the time that PIXL data were acquired. So that can give you a sense of the microcrystalline texture. Panel C corresponds to the target Guillaume that you can see on panel B. Panel D is the Bellegarde target, and then on a return, we ended up sampling another abraded patch, which is shown in panel E, called Montpezat. The panel E actually shows a bit of lingering dust that's produced from the surface abrasion. So the last stage of the surface abrasion involves a burst of gas that allows the dust to be cleared apart. That blast of gas is only partially successful. So the PIXL data were acquired on the most obviously dust-free regions of that panel E target. Okay, and then we'll go to the next slide, and I'll show you some really interesting compositional and textural data. There's a lot of information captured in this plot, and so what I'll do is I'll walk through this step by step. So what we're looking at is we're looking at PIXL data sets from 3 different abraded patches, so the 3 patches that I mentioned in the previous slide. Before I talk about the textures and the different colors and boundaries represented on the upper panels, I'd like to just draw your attention to the bottom ternary plots, which actually is a nice place to start in looking at the bulk geochemistry of these targets as observed by PIXL. So these bottom ternary plots are constructed in molar proportions of calcium, sodium, and potassium on one axis, silicon on the upper axis, and iron and magnesium on the lower right axis. And this is useful because it captures most of the major elements of rock-forming minerals and allows you to relatively rapidly identify mixing relationships between mineral end members. So you can see plagioclase minerals and pyroxene and some other minerals of note, their ideal compositions illustrated by the black circles. The entire data set, so all of the pixels are plotted in gray, and some of those pixels are highlighted in red, or it's sort of a reddish orange. Now, I'll say that our interpretation of the data in combination with data from other instruments shows that these are igneous rocks. So these are effectively basalts dominated by plagioclase, pyroxene, and smaller amounts of olivine, of iron-rich olivine. You could see that manifested in the gray scattering on the ternaries. What's interesting about this, though, is that there are regions of these rocks associated with very high iron and high silica content, and not much else in the way of other elements. So essentially no aluminum and relatively small or minor amounts of magnesium. Those are illustrated in the red orange points on the ternaries, and their compositions lie between end member olivine and hissingerite, which is a ferric iron serpentine mineral I'm sure many of you are familiar with. Now, those orange points correspond to the regions of the maps located in the upper panel outlined in white. So everywhere you see white regions outlined in the upper panels, that corresponds to material that is highly enriched in iron and silica and not much else. So very low aluminum and very low magnesium. In addition, on these targets, I have diffraction data overlain, and the diffraction data are shown in sort of a muddy brown color, which indicates no diffraction observed, and then either blue, green, or red, which indicates mainly diffraction from olivine. Now, starting with the upper left-hand panel, you can see a region dominated by material that's compositionally similar to some combination of iron silicates, that contains within it largely non-diffracting material, so either a very finely crystalline or poorly crystalline in nature. And then there are some regions, some localized regions that display coherent scattering or diffraction from olivine. Actually, in that first panel, some of it is a little bit grayed out by the overlay, so you can't really see it so well. You can see similar relationships in the middle panel. And then also on the right-hand panel, there are really some fascinating observations. So you can see regions outlined in red and blue, which correspond to diffraction from olivine in different orientations. But you'll note that there are 2 regions in red that illustrate diffraction from olivine and olivine scattering domain in the same orientation. Those two regions are actually cross-cut or dissected by material that is rich in iron and silica and is non-diffracting. And in this location and several others, we've compiled evidence that olivine has actually been dissected and variably replaced. And in some cases, we interpret completely replaced by this material that is extremely high iron and high silica in composition. Okay, so could I go to the next slide, please? In addition to the compositional and textural data and the information that we get from diffraction, it turns out that backscattered X-rays end up giving us additional information about the nature of materials that I've just described to you in the previous slide. And so backscattered X-rays are X-rays that are scattered back, so they're neither fluoresced nor diffracted. And the efficiency of that backscattering is actually proportional to atomic weight. And so basically the backscattering X-rays that we're quantifying here, which originate from the rhodium L line, indicate that the olivine alteration products that I've described to you happen to be enriched in low Z elements. So by low Z elements, we mean elements below the lower energy limit of the PIXL instrument, so dominated by oxygen and hydrogen, but potentially carbon as well. It's difficult for us to distinguish between those possibilities. In addition, this spatial distribution of backscattering is consistent with generally low element totals of this alteration material. So the totals that we've derived from the PIXL instrument, when they're corrected for diffraction effects and also roughness effects, lie in the range of about 85 to 95 weight%, which would be consistent with the interpretation that these materials could be dominated by iron-rich serpentines, a common alteration product of iron-rich olivine. Could we go to the next slide, please? And it actually turns out that another constraint on the mineralogy was derived from another instrument on the Perseverance rover. So this is the SuperChem instrument, which is a remote spectrometer that has capabilities, imaging capabilities in the infrared. And the infrared spectra obtained by the SuperChem instrument on footprints that overlap with the PIXL scans indicate that the material that dominates the IR signal is in fact a hydrous iron-rich silicate. The IR absorptions identified by the SuperChem instrument can either be explained by nontronite, which is a ferric iron dominated spectite, or hissingerite, the ferric iron dominated serpentine that I mentioned before. It's actually very difficult to tell those two apart because they have nearly identical spectral properties in the mid to near infrared. That would be consistent with the PIXL data that I mentioned in the previous slides, but it's useful to note that only hissingerite would be consistent with the iron to silica ratios that we've extracted of this alteration material as measured by PIXL. So although nontronite could potentially be present in the PIXL scans, the PIXL data suggests that it's not a major component, and instead hissingerite would be a better fit. And could I go to the next slide, please? And one last important feature to note here is that the olivine that appears to be altered in these targets, along with the alteration products, is associated with relatively high manganese compared to the rest of the materials. So I've got a couple of plots that show this for just two of the targets that I mentioned before, but these relationships have actually been observed in all three, and actually a fourth target from this formation. But in general, the olivine is associated with higher manganese and a distinct iron to manganese ratio from the iron silicates, which are altering it. So this suggests that that serpentines may end up dominating the secondary mineralogy from the olivine, and are in fact inheriting some of the manganese that's present in the parent olivine. Okay, so just moving on to the next slide, I'll just sort of recap some of the major points that we have interpreted as in situ evidence of serpentinization of ferroan olivine. So the combined compositional constraints, the diffraction, indicate that phaelite, so these olivine compositions are largely toward the phaelitic end, has been dissected and variably replaced by a poorly crystalline material that appears compositionally identical to iron serpentine. The rhodium backscattering analysis that I mentioned before and the corrected element totals indicate that the iron silicate material is in fact hydrous. And additional constraints from the SuperCam infrared instrument suggest that this material is likely to be dominated by materials like hissingerite, which would suggest that the olivine has in fact been serpentinized. And what's interesting, and I haven't really had time to discuss this in part because it's a new result, but forward modeling of element mixing relationships in combination with rhodium backscattering analysis and UV spectral properties from the micro context camera that PIXL has on it actually suggests that magnetite is likely associated with olivine and some of the iron silicate rich material that I've discussed before. So it turns out that magnetite actually has relatively distinct UV spectral properties that help differentiate it from other potential iron oxides. So this is an exciting possibility, and we're working on these results at the moment, but it's possible that magnetite could be associated with some of these processes. Now, it's a different matter entirely for us to conclusively demonstrate that the magnetite is secondary in origin and not an igneous spinel, but we're going to have to work those possibilities in tandem. Okay, so moving on to the next slide, please. So the major question is, if olivine was serpentinized, what then drove this style of alteration? So where could the fluids be coming from, and under what conditions might this be occurring? I think in terms of conditions, we're not really able to constrain things like temperature in any significant way. That's mainly because the iron serpentines relative to olivine have a relatively large stability field. If we can conclusively demonstrate that magnetite is secondary in origin and associated with the serpentines, and we may be able to better constrain temperature of alteration. But qualitatively, some important information has come from comparing the style of water-rock interaction in the Maaz Formation, which I've been discussing here, to another formation called the Seitah Formation, which is directly adjacent to the Maaz Formation. And the Seitah Formation, as was documented in the journal Science earlier this week, is an olivine cumulate. And Mike Tice's paper describes PIXL data that presents evidence for the style of water-rock interaction within those olivine cumulate samples. And the PIXL data indicate that fluids infiltrated cracks and voids and altered some of the olivine dicarbonate and low iron and magnesium secondary silicates. And in general, this is a style of water-rock interaction that's unlike the Maaz Formation in the sense that the extent of olivine alteration from what we've seen is generally limited, and the distribution of secondary materials is generally confined to intergranular pore space. And that's actually quite different from some of the textural evidence that I presented in earlier slides. This suggests that there was potentially a different process that affected only the Maaz type of lithology. So now we're talking about two very different lithologies here: an olivine cumulate that resides in the floor of Jezero Crater, and a relatively fine-grained basalt that's quite iron-rich in composition. And if we go to the next slide, because these two units are adjacent to one another, it's difficult to explain all of this process by very low temperature sort of chemical weathering style alteration, simply because we would expect that the rest of the rocks would display geochemical signatures more consistent with chemical weathering processes. We can't conclusively rule that out, but qualitatively it suggests that there's a style of water rock alteration that seems very different between these two lithologies. So moving on to the second to last slide here, one possibility, and this is just a hypothesis that we're working now, that might explain the differing styles of water rock alteration as a function of lithology, could relate to post-crystallization history of this relatively iron-rich basalt. And one hypothesis is that the water that was actually doing the serpentinization could have been exsolved during late stage crystallization. And we started working with some of the igneous petrologists on the team to really explore this possibility. I mean, the basalts that we've been discussing here are very iron rich, and they have relatively higher silica than the olivine cumulate. And so by that standpoint, H2O should be relatively insoluble in their parent melts compared to, say, the parent melt of the olivine cumulate. We don't know exactly, or actually we don't know very well at all what the water composition of the parent melts might have been, but we can estimate what's known from the Martian mantle, and then we also have some constraints on accessory phosphates from the olivine cumulate that suggest that the parent magmas were actually quite dry, at least the parent magma of the olivine cumulate. In any case, it suggests that depending on the pressure of emplacement, the solubility of H2O could have been surpassed at relatively late stage crystallization. And so that could potentially be enough to stabilize a supercritical fluid, which could potentially have serpentinized the materials that I've talked about here today. So again, the pressure of emplacement of the Maaz Formation is not very well constrained, but this is a hypothesis that we're working now that could explain the differences in the style of water rock alteration that I talked about today. Okay, so I'll leave it there and would welcome any feedback or comments or questions, but I'll just end the slide with a recent picture of the PIXL team. And just to say that this has been a real team effort, from both sides of the team, the engineering and the science team. And the data and interpretations that I've talked about today are really the result of a lot of hard work by a lot of extraordinary people. So thank you very much for your time, and I'd be happy to take any questions.